皆さん。
Good morning. First of all, I would like to thank the host of this event, giving me such a great opportunity to speak to you. Listening to the presentations, there was a history of the classic computer development. In the middle of the 1970s, I have been using the classic computer until now, so it was quite interesting story. And to be honest with you, the quantum computer I have never used directly. I am pretty classic person, and however, I will be speaking about the quantum computing, so it will be quite interesting. So the title would be Coherent Quantum Annealing, and using the coherent quantum annealing, the large size of the quantum simulation. That's what I'm going to talk about it. One is a coherent quantum annealing, and the second is that the large size volume of that quantum simulation. I will be focusing on those two. And in a few years, or maybe in a few months or so, there was a big development, and I'm going to make a report on this. Now, this is what I would like to talk about first. A month ago, what happened was that there was a conference that we hosted, MIT, Professor Dr. Seth Lloyd. He actually showed this graph, and it was quite interesting. And for this quantum simulation or the coherent annealing, and this presentation, this is going to be the basis to understand the quantum science and technology development. And that is the reason why that I am showing this to you. In 2022, and we're going to be in the NISQ era, and ultimately, our goal is going to be fault-tolerant quantum computer. We don't know when it's going to be established. It could be like 2030s, or maybe later than that, or we may never be achieved, unlimited or infinite. That's what he said. So in either way, this is where we are targeting for and putting every effort to achieve this as researchers. So until this journey completed, well, not just the narrow meaning of the development of the technology, but also there is expectation from the social as well as the investment for the social. There is going to be the time that will experience plateau or may reduce, and that's what he described as a quantum chasms. So what is very important is that how we can actually activate this area. And we have to find a good direction for it. And we have to be activated as researchers. And then also we have to come up with some kind of strategy so that the expectation from the society is going to be bigger. And that is also a common message that we're talking. And now we see some signs here. And one is a quantum simulation. That's what the doctor said. And the quantum simulations, or using the hardware for that. And that's what he had in mind. But today, I would like to talk about quantum annealing. In the past few months, or maybe in a few years, we made or we can make a large development. So that's what I'm going to talk about. And I will be talking about two. And the first is a quantum annealing overview. I will be explaining that, including what is the challenge and problem. And the latter part, and based on that, I will be discussing about the coherent quantum annealing. The technology has been realized, and then using that, we can actually do the large volume of the quantum simulations, which has not been published yet. And first, I would like to discuss about what is quantum annealing for. And The first point is going to be combinational optimizations. And at the same time, the actual device, DBM quantum annealer, is going to be used. And the less energy solutions, or the answers that we will be able to achieve. And sometimes you may get the solution and answers, which is a little farther than that. But we can actually use that Boltzmann machine learning with this approximate solutions. And that sampling is happening. And then also the quantum simulation, that's where we see the drastic development. And simulations, there is one in the classic computers, but in the quality, this is different. On the classic computers, when we say simulations, there's a physical phenomena, and that is going to be converted into value of the figures. So the combination of the 0 and 1. And then that is going to be processed in high speed. And however, in the quantum simulations, for example, the chip of the quantum computers, and directly we will produce that phenomena and then try to understand the mechanism. And with that, we would like to develop a new things, physics. And therefore, this is more testing, or I would say this is a testing or experiments. So in a few years, I have been focusing on this, and I see a very exciting things here. And I would like to share with you this enthusiastic feeling with you today. And of course, that there is a lot of problems, the issues. And for example, there is a D-wave device issues, or some of the devices has under development. And one of the issue is that limited numbers of the qubits, and 5,000 is a limit as of now. And then if we want to get the issue, want to solve the problems for the societies, and it's not sufficient at all. And also the finite connectivity between the qubit. In order to solve the social issues, problems, the between the qubit, and that have to be connected, but it cannot be. If you want to do it, in that case, the finite connectivity between the qubit, and there is a limit on that. And effective qubit numbers is reduced. And next problem is a noise effect and parameter migration, because there is a thermal noise, and then also the noise coming outside. For example, crosstalk. And it should not be connected, but in between qubits, there is interference. And that becomes a noise. And we have to solve that issue. And then also the parameter migration issue. If you set the parameter to the certain values, and because this is an analog elements, and therefore, and it will fluctuate. And later on, I will show the data, and this impact very severely in some cases. And those are the problems that we are facing. And there's a three problems I have talked about it. And not just for the quantum annealing machines, but for the gate type, because it's an analog device, and therefore these are the problems that they are sharing as well. And this is a problem that a lot of the researchers are trying to come up with a solution for this. That's challenges. And now, and I would like to show the evidence of the thermal noise, and this is from the 6 years ago, and Google was doing this kind of research. And horizontal, you see the temperature, and the vertical, and this is a probability for the right answer probability for a problem. And the blue is a D-wave actual data, and the red and brown, is based on the theory of the finite temperature, and this is based on the finite. And this is not the absolute zero. This is with the theory of the finite temperature. And the wave output, it matches very much. And for example, a D wave device, because of the coherence, it could be like a classic machine. And based on that assumption, this is the data that we have received, and that is shown in green, based on the classic theory. D-wave device, this is 6 years ago, so maybe a second generation, the third generation before. And then based on this, the quantum theory, it actually runs. However, there is the impact from the thermal. So incoherent quantum annealing, that has been established as of now. And therefore, ideally, we would like to get rid out of those noise from the thermal. What do we do? And we kind of find out what to do with that. And that is going to be the part of the my discussion. And there's other issues, calibration problems, which I would like to talk about now. This data, and that's in our paper. And the spin index from 1 to 2000, which is horizontal. And the vertical is the average magnetizations. So in qubit, there should be no interactions, and then also there should be no bias for each qubit, and therefore there's going up and going down bit, and then actually this has to be zero. But when you measure, as you see the purple area, there is lots of the fluctuation or disbursement, and from 0.2 to 0.3, around 0, there is I would say that this is bad data. And if we use this, and in that case, a very small, compact, or very accurate simulation that we cannot get it, and therefore we have to calibrate. And for example, with the plus data, and in that case, the minus bias is going to be applied. And if the qubit with the minus data, in that case, with the plus bias to make it zero. If you do that in a case, you will get the green part. And this is output that we can receive. And so that ideally it will be zero, but it's pretty difficult to achieve zero. But we need to do this in order to get the accurate the data from the quantum simulation. Of course, as a device, people do the calibration sometimes. However, yourself, when right before you use the machines, you have not done the calibration. There's no guarantee, right? Somebody was doing calibration sometimes. And therefore, if you want to do the computation, and that's where the accuracy, severe accuracy is required, or the quantum calculation. In the case, this is going to be the challenge that you have to overcome. And if you're interested in it, please refer to this data. And now, in the same paper, I've talked about before and then after calibration. What is the effect of the parameter? Now, the after, it's going to be much cleaner data. So, as I've discussed first, in terms of what to be done to a solution of those problems, the hardware improvement, and more qubit and connectivity conference time. And many experts are working on this. And then development of quantum classic hybrid algorithm, because we don't have sufficient numbers of a qubit. And the next one is going to be today's topic, to identify tasks that need a very short time to minimize noise effect, so that we can avoid a thermal noise. And the next one is the parameter calibration, and those are the direction for the solutions. And this is what we are going to talk about it today. And this is the latter part. And I have been discussing about the overview of the framework. And there's the papers, and out of 3, in terms of the 2 papers that have been involved. And need to talk about the physics in order for you to understand what we have done. I will explain very simply. And this is the quantum-based transition, the theory that we have studied. And the status changes drastically. The H2O for the waters, and those molecular for H2O molecular is working around in the containers, and that is the water. When the temperature goes down, and there's the 0 degree, and then there is going to be the quantum phase transition, and that makes the water ice, as you know. And if the gradually temperature goes down, in that case, you can get the crystal of the snows. But if you drastically reduce the temperature in that case, there will be some defect. You may have the very clean, the beautiful, the crystal of the snow, but in the other areas, we may get a defect. So this is a function of the speed of the cooling. And so keep like a mechanism. That's what I have explained about it. So this controlling the temperature, the status will be changed. And quantum, the phase transition, that happens as well. And in this case, what is going to be a control is that slow reduction of quantum fluctuation. And if it's bigger, and then that is going to be totally disordered. And at some point, it will be partially ordered. And there is the quantum phase transitions. And then there is the mechanism in the quantum world as well. And we have done the calculation. We don't have time, so I will just show this to you. And with this theories, and we have studied, and actually one of my staff was going out, and then there's only a 1 month left before he actually go to the other positions. And then therefore, if it's a first chain, that would be easier. However, still it requires more deeper the studies, and there was a great outcome that we have achieved. And you see the computation time in numbers, horizontal, and the direct number of the effect, and which is the vertical. And from the D-wave device, there is the output, and there was two places. If you see the shorter ones, that exactly is same as the theory, from 1 nanosec to several tenths nanosec, and there's no other thermal noise. But if it get longer, and then the data is going to be disordered because of that impact. And then within the some second, some tenth second, nanosecond, and in the case, there is no impact. So in a shorter time, the scale up to tens of nanos, and data agrees with the theory, and that increased noise effect. The device realized coherent quantum annealing. So that's exactly is matching. And I think that this is the first case to run the large-scale artificial quantum device with a 2,000 qubits noise-free. And we cannot actually do this in the classic computer. But using that quantum multicolor law, we can simulate, because that's not depending on that time. In the parallel case, that is correct. However, if there's a dependency on the time, or for the dynamical the problems, in that case, it cannot be done with the classic computer and the Monte Carlo method. It is not possible to do it. And in 2000 qubit with the shredding method, it's not possible to do it. And therefore, it looks like this is very different. However, because of that, 1D chain. Therefore, even though with the classic computers, we'll be able to do it. And that was quite interesting. And a month ago, in the meeting, and D-Wave people made a report. Using the same method, the 3D, the layers, and which is a spin glass, which is a complicated the material, the coherent annealing, quantum annealing, they have studied and tested the theory, and with the 3D spin glass, and that is very complicated in the case. Even though whatever the method is used, 5,300 bit system simulation is not possible. So the spin glass, and there is a typical hard problem, and the quantum simulation was actually conducted in this area. And the spin glass, and this is academic issue, but the technical barrier is going to removed, and therefore, furthermore, it's going to be more. We'll be able to apply this for more significant social other problems pretty soon. So this is going to be the last slide. And the basic research for the quantum annealing is drastically advanced. And this is the numbers from the basic research papers. And it is increasing in an exponential manner. And this is from the Google Scholar data. So the rapid increase in basic research in recent years, and that means it will reflect to the better result for the real-world problems in the near future. Thank you very much for listening.